So today I want to talk about how to model consciousness processes in the categorical process theory. So this is joint work with Elias. Uh, so, so first, what is categorical process theory? I think Robert mentioned process theory. This categorical process theory is the basic idea is okay. So everything in the world can be seen as a process, no matter it's a mental process or a physical process. So it always can be seen as a process. And then we want to use, once we have some processes, we want to compose them into more complicated processes. And the way we compose the processes basically are two. Basically, there are two ways. One is the sequential or called time composition, and one is parallel or space composition. So all the other compositions can be built from these two basic compositions. So I will explain how. That's the basic idea. So okay, so we want. So once we have this basic idea, we want to use a general framework, mathematical framework, to describe the processes. So first, so we denote any process which is a change from type A to type B. It doesn't matter what it is, we will interpret it. So I usually read a diagram from A to B. So use a box to represent it, and then this process can be composed with another process sequentially. So that means if we do one thing first and then do another thing, then these whole two processes can be seen as a single process, which means a single process which means these two things happened sequentially. So in diagrams, you just draw these two boxes together, but they should share the same type in the middle. And another way to compose them is parallel composition. That means, okay, so two processes can happen simultaneously. So these two processes happening simultaneously can be seen as a single process. So in this way, we compose them as a big one. And then another thing is, okay, so when you set two processes, they happen simultaneously, you put them in parallel. And then, but when we write down them in a paper or whatever, in a plan, then the problem is, okay, so which one, it should be, physically it should be, essentially it should be, doesn't matter which box put on the left or on the right, right? But when you write down them, one have to on the left, one have to on the right. So there is asymmetry. So how do you deal with this? So that means, okay, to make this theory well, so we need to introduce a symmetry process, which is swap. And that means, okay, if you swap them, you swap these two processes, and you want to make it essentially the same. So they should be the map or the type should match. A, C, D, B should match, and then they are the same. That's essentially the same. So that means we need a symmetry for this process theory. Okay, that's done. That means, okay, then so then in categorical language, this means, okay, these processes, very general processes, can make a symmetric monoid category. That's for sure. So, but the problem is, okay, so for general process, you can make a category, but that's an box. That's not enough to know what is inside. So what is the process really is, right? We don't know the details. To fill in the details inside the box, so we need some, so the way we deal with it is to use some more very basic processes, right? There's yeah, I have same, I didn't say, but I have the same point of view as Chetan. Take consciousness as fundamental. So there's, I don't think even there is no fundamental like partics, real partics, but there could be fundamental processes. So here we want to use some very basic processes, so which we call generators. So this is a spider, and this spider. So why we choose this, I will show later. So there are two different color spider, and this black notes, and this dimension. Every wire here is the same dimension, the same type, but here they could be different one. So and there's the identity one. That means nothing happened, and there's the swap we just said. Okay, so with these basic processes, what can we do? That means, okay, we can use basic processes. The idea is, okay, we want to know the details of each processes, and then we want to use these basic processes and to compose more complicated processes. For example, if we can compose these kind of things, two different colors, they have multiple wires, they can connect together, and this is another way to connect them. And then we can make it even more complicated. That means, okay, we can put different things all together like this. So then this become a big process. So that's the way we want to build all the details for the processes. But the thing is, how do you reason with it? So once you just have processes, it doesn't make sense, right? You need operations. So how do you deal with them? How do you transfer this? Because they are changes. How do you transfer? How do you describe the transformations? So basically, the basic way is, okay, we do it in a local way. That means we do rewriting for diagrams. So for example, if we have this diagram here, and rewriting means, okay, here for a part of the diagram, we substitute this part of the diagram with another diagram according to an equality of processes. So then you got this one. So just because these two are equal, and then that means if you replace this one with this one, they're still the same, the whole as a whole diagram. So that's how you do rewriting. And then so for example, if we for now diagram like so here we use this as a basic generator, then one typical rule we have is we can fuse the same colors thing, and then here you got they are fused, and they are also symmetric. And this is another rule we call bijury, but anyway, that means, okay, you can if you connect this way, they are the same. This means this like eigenstate, they can be copied. But anyway, this example I just want to show you, that's examples of the how the rules of diagram looks like. And so at the moment, so next we want to show that so how to represent, but if you consider a concrete category, whatever it is, how do you represent them in diagrams? So it really depends on the which concrete category you are working in. But the basic idea is so first you make you want to make the concrete processes you are considering whatever into a symmetric monodic category, which is very easy to make it. Just use the two basic compositions, and then you want to interpret the diagrams for general processes. You want to interpret them into this concrete category. Mathematically, that means you want to find the symmetric monodic functor to map to the concrete category from diagrams, the category of diagrams. And also, if you So if you want to represent every process by diagram, that means you need to make this functor, interpretation functor both surjective on objects and morphisms. So that's the general way you can find the process, how to represent process in diagrams. But how do we know? So how much loose? We have so many loose. How much loose is enough? So, what are enough loose means? That means whenever two diagrams they are equal under the interpretation functor, you interpret the diagrams under this interpretation functor, and then that means in the concrete, if they corresponding two diagrams, they corresponding to the same processes in your concrete category, you need to be able to use the rewriting rules to rewrite one diagram to another, right? That means if you can, that means you don't need any concrete things. You can just do diagrammatically. Then that means it is enough. So categorically, that means you need to have enough rules to make the interpolation functor feasible. And then, okay, so I want to show example. That's too how to say abstract. So I want to take the concrete example category as the category of finite dimensional Hilbert space. So the objects are finite dimensional Hilbert space, and the morphisms would be the linear maps between them. And then, okay, so very recently, so we use these spiders generators, as I just showed, to prove that, okay, so actually we can use this if we choose the concrete category to be finite dimensional of Hilbert space. Then that means we can reconstruct the quantum theory. Of course, for finite dimension, I will mention a little bit of infinite dimension later. So because then we can prove that this category of diagrams is equivalent to the category of finite dimension Hilbert space. That means, okay, you can just use these diagrams to do everything in quantum theory. So how do we did it? So basically, okay, as we said, we choose the generators. These are basic generators on the diagrams, and then we interpret in this Hilbert space. So as this. So I don't want to show the details, but just let you know that, okay, this there existed. And then, so actually I also want to mention that although we are saying that we can do reconstruction of quantums, actually this framework works on, I mean each diagram corresponding to linear map. Actually, the linear map usually in quantum theory works on the linear map is over compressed numbers, right? Compressed numbers. The field of compressed numbers. But actually, it works for the coefficient can be any commutative semiring. Yeah, so a typical example of a commutative semiring is the set of natural numbers with addition and multiplication. So it works very general for actually commutative semiring, actually. Also complete. So you can interpret it in this way. And also, how about the rules? How much is enough? That means you need to prove the completeness. So we have this, then we have this kind of rules, which that means, okay, you need a spider fusion and for the red, green and red, and then you have some rules. I don't want to explain all of them, just want to show you that, okay, there is a way, the very typical way to show how they could be complete. This is another rule, that means for this part, for this is both mostly green and red, and this is about the black and the green. How do they interact with each other, and this is how the three things, the red, the green, and the black, how do they interact with each other. And also because we want to make them interact with different types or different dimensions, and we also need to know how this one is the dimension box, how the dimension box interact with the green, red, and the black, how to interact with them. Like for example, like you can see from here, this means this box is a unitary. But anyway, so that means okay, we take this as example. Take the we interpret these diagrams into the category of finite dimension Hilbert space. Then we got the reconstruction of quantum theory. That means you can recover the quantum theory in finite dimension. So that's the example to shows how do you how do you use this process theory to represent, okay, thanks, to represent the processes. And also I think because the quantum theory is related to the consciousness, but so that's why I show this as an example. And then I want to show a little bit that so we also have another program, and this is the first work. That means the previous one we reconstruct. We use processes, basic processes, just two compositions, sequential and parallel composition, space or time composition. Just use them, we can reconstruct quantum theory over finite dimensional Hilbert space. But how about? But people usually ask, how about the infinite dimensional Hilbert? Usually quantum mechanics is about infinite dimensional Hilbert space, right? So how do we deal with it? The basic idea is so we showed in this paper. We present at QPR this summer. The basic idea is okay. So if you can see the infinite dimensional things, so usually you want to use diagram, process diagram, to represent them. Usually it's very hard. So you need to even like the usual very simple like Yankee rule doesn't hurt there. So the basic idea is okay. We want it's not good, but we truncate it to limit the dimension. So we truncate from infinite dimension to finite dimension, and then we can use all the rules there, and then we leave the back, use the linearity. That's the basic idea. So that's how we want to deal with the infinite things, infinite dimension Hilbert space. So we hope to use this idea to, and this kind of diagrams to recover the general quantum mechanics things. That's the hope. And how many minutes do I have?
2 minutes.
Okay, so I want maybe very roughly say that okay, so we can interpret the diagrams in Hilbert space for quantum theory, but how about if we interpret in another space? So what we tried in this paper is we interpret diagrams in conscious experience, but this is just the beginning of the work. So there's lots of work need to do. And very roughly, so I want to mention something like that recently there was FQ XI competition. I found a very interesting essay, which is the first place winner. So they mentioned the problem of subject and object split, and so I would hope. So object, that means they can't perceive anything, just present some information, but subject don't present any information, they just cognize objects. So we would hope to use this thing to represent, like subjects, like objects, we want to use diagram to represent this subject and object. So like for example, the objects usually can be images, right? Sounds, smells, tastings or touches. But basically, for example, for images, how do we deal with it? Represent it first. Usually we use multi-dimensional array, right? Like here, dimensional array. So this one is actually just actually this. Doesn't matter the direction of the types. So basically, it is just a tensor. So multi-dimensional array is another name for tensor, and you can use those diagrams for any tensor with different dimensions. You can represent with those generators I just showed as this diagram. So possibly, if you represent, so for me, this kind of thing, this W, they have no information. They can see modeled as a subject. And the other things can be like this, and this can be encoded any information, so they could be interact with each other. Then you got the whole picture. So we are hoping maybe we can use this way to represent the subject and object interaction. Yeah, so that's a rough idea. Yeah, that's it. Thank you.